Every 6 months we come out here and measure from a constant elevation the distance to the marsh surface from this table. And what we do once we put the pins down to the marsh surface, and I've already done that, there are 9 pins, then we measure the distance from the top of the pin down to the table. And of course the idea is that if you measure this the same place every time, you're going to over time get a change, either an increase or a decrease in elevation. Yeah, so this is a piece of irrigation pipe that's been pounded in with a vibrocore up to 3 meters in depth to refusal, and that's considered to be the Pleistocene platform. And then within that we've cemented in this tube that has 4 positions on it, and so that the arm can be put in the same position, 4 positions every time we do the measurements. And then there's a bubble level here that we make the whole platform or the whole table level, so that when we drop the pins down that they go to the same place more or less every time. China Payton's marsh, you can't see the surface, so you actually have to feel the surface. You bring the pin down until you hit the spongy surface, which is actually a root mat, and then that's where you stop the pin. So what we're seeing here is not deposition of sediment, but rather accretion or deflation as a result of changing root mat. So the organic content of the marsh here, marsh surface, is nearly, I think it's right around 80% organic matter. .8, 20.7, 19.5. We have 4 places in this particular marsh where we're doing the measurements. One along a creek bank that goes up to the marsh platform, one in so-called low marsh, one set in the mid marsh, and then this 3rd set up in the high marsh. And the reason and each of these has 3 platforms or 3 sites where we're measuring this whole series. The one here is set up so that we're having a situation where the marsh is collapsing, and we want to capture that collapsing as that marsh collapsing moves in this direction. What's happening up here, we're not sure of the cause, but we're developing a hummock and hollow situation, so there's more and more open water, and the Spartina patens is not that well adapted to flooding, even though it's a wetland plant. And so persistent flooding is not something that it's well adapted to. So you get, if you get any kind of rack deposition or heavy grazing by muskrat, then this opens up the area to this hummock and hollow development, and eventually we expect the organic matter to be largely lost from this area, and then the tidal creeks to move headward and essentially convert this to a low marsh. So with the collapse of the marsh surface due to oxidation of organic matter, that's essentially a relative rise in sea level by comparison. So in some ways you can think of this high marsh setting itself up to become a low marsh, or for tidal creeks to come in here. At high tide right now, so much of the structure of this tidal creek is underwater, so we can't really see it. But wanted to point out here that this tidal creek is eroding headward into the high marsh. So there's a fairly steep scarp here that is now underwater. And you can see the transition from Spartina patens dominance to Spartina alterniflora here along the creek bank. This headward erosion in many places in the VCR is occurring, it's actually following antecedent stream channels that were there during a low sea level stand. Following these headwards, that's the weakest point where the deepest peat is, and of course that's where the tidal creeks tend to go to. So we expect eventually this intermittent open water, the hummock and hollow area that is very rich in organic matter, to eventually get connected with this tidal creek, and in that way it'll become a tidal system instead of one dominated by precipitation. And of course when that happens, you have a change in species composition from the high marsh species, the juncus and the Spartina patens, to the Spartina alterniflora.